Up next, we have Jonathan Schrader, who works with the geographer at the IPM Center for Data Integration at the University of Minnesota. Go Gophers! So thanks so much for joining us, and he'll talk to us about IPMs. I believe is IPMs, correct?
Yeah, correct. Thank you. Let me share my screen. I think I got it here. All right, I think everyone sees my screen okay right now, the first slide.
Yes, you're good. Thank you.
Yeah, looks great.
Thank you. Happy to be here today to give you a big overview of all kinds of geographic census data resources that we have available through IPMs. I'm calling this a whirlwind tour. As it happens, this month marks the 25th anniversary of my starting as the first graduate assistant on the NHGIS project back in 2001. And I've been reflecting a lot on that. I've given a couple talks this month, and it's been a real pleasure to look back and give these big, broad surveys of everything we've accomplished. And of course, IPMs USA, our microdata project, goes back even farther. It's a big ecosystem now. We have all kinds of things that can help census data users, not only using historical data, although that's a big motivation for what we've provided, but also using contemporary data. And the way I'll proceed is just give you the initial background on who we are, what we're up to, and then I'll dig into first the project that I manage, NHGIS, where we provide summary tables, GIS files, time series, and crosswalks for US censuses. And then I'll give a briefer overview of what we provide through IPMs USA to help with geography and census microdata. And we'll have a little time at the end for questions. To answer this question, people often wonder, what does IPMs stand for? It's the Integrated Public Use Microdata Series, or more exactly, it used to be that. Once upon a time, IPMs only provided microdata, and it only provided public use microdata. Now, IPMs is what we use to describe all of the data projects here that used to be managed in the Minnesota Population Center. We've moved them all out of that and into their own data center, where we can focus on providing data here at the University of Minnesota to researchers all around the world. And that includes things that aren't microdata and even some things that aren't public use. So IPMs is just a name now. And if you're familiar with Esri, who creates GIS software, you will be familiar with another acronym that used to mean something specific, but now it's just a name. We are a data provider of both US and international data. We provide data mainly for censuses and major national surveys that we've obtained from, the US Census Bureau or from other statistical agencies around the world. And what we really try to emphasize is not just bringing this data into one place, but also integrating it across time and space, standardizing codes and concepts and documentation and metadata and access systems so that you can get it all in one place in a standard way. That means that we're not just data, but we're also websites and data access systems. We also have documentation, and we are also a pretty big group of people here who are available to give talks like this, but also to answer questions if you have them. We have a couple different user support channels that I'll share at the end of the talk. Here's our main website, ipms.org. Immediately, what we foreground here is that we're actually a bunch of separate websites that each provide different kinds of data. You can see all the different visit site buttons there. And to zoom in on those, it's a grid of 9 main websites. Most of these provide microdata. I'll provide a definition of that a little later. I'm sure a lot of you are familiar with that concept, but maybe some aren't. A couple of these provide summary data and lots of GIS data as well. I'm going to focus on these two. IPMs USA provides US Census microdata for the decennial census and American Community Survey, and NHGIS does the same, but with summary data. and GIS data for the census and ACS. So that background, most of what we've been talking about in this GeoForum are summary data and GIS data because we're interested in geography. And you can get a lot more geographic detail with summary data. This is an older version of the census's standard hierarchy of summary levels. These are each different types of observation units in summary data. It's basically data about areas. It's summaries of the population and housing in each of those areas. The microdata is data from each individual respondent at the household and person level. Exactly which age, sex, race, and occupation, educational attainment, etc., was reported for each individual in a sample. In the public use microdata for recent ACS and censuses, it's greatly restricted in detail about geography in order to help prevent you being able to identify. It doesn't include everybody, it includes a sample, and it doesn't identify everything about that person down to where they live, or else you'd be able to identify too much. But with that sample, you can do all kinds of flexible classification, modeling, and cross-tabulation. So microdata provides a lot of power. It just doesn't provide as much geographic detail. And I'll return to that at the end of my talk. Where I'm going to start is with NHGIS, which provides the summary data and GIS data for census areas going all the way back to 1790. Here's an example of some maps using 1840, 1940 county level data, and 1940 tract level data as well within each of these highlighted cities. We have in NHGIS, we have data for both summary tables and boundary data all the way down to census block level. We have also our proprietary unique data products, time series tables and geographic crosswalks that link data together across time. In this map that might be of interest to some of the census employees, we're showing the change in the young adult population share from 1990 to 2020. You can see it grew a lot in central DC and declined pretty much everywhere else. And we're doing that in consistent units, 2010 block groups. As has been discussed, or it came up in earlier talks, these units, their boundaries change every 10 years. We have produced data that's standardized to just the 2010 units, and I'll talk more about those later in my talk as well. An important caveat is we are a data source and not a mapping or analysis tool. The GIS in the NHGIS name might make you think you can do GIS with our website. Actually, you can get data that you can download and then load into your GIS. We have geographic information. We are a system, but we don't have analytical tools. Here's an older map that Kyle Walker created, an online exploration tool using ACS data that he obtained from NHGIS. We don't have something like this on our website, but we do have the data that allowed Kyle to make that map, both the boundary data and the summary tables. You can also get this from the census website, as many of other presenters have made clear already in this GeoForum. We have some unique features to our website, and of course we also have historical data, which is a reason why some users prefer to come to us for this type of data. We also have nationwide extents for most levels, including the GIS data. That is a little unique because I think the Tiger line data and some summary data at least used to be only available for particular counties or for particular states, but here you could get a block group level GIS boundary file for the whole country. And another bit of good news is that we have continued to be, so far, funded by NIH and NSF grants, which allows us to provide all of this for free. So just like the Census Bureau, you don't have to worry about paying for us, except through your tax dollars. I appreciate that. So quick walkthrough to see how this all works through our site. You could go to the NHGIS main page and click the Get Data button to enter our data finder, where you will find there are 3 different data types listed. You can use these buttons at the top to restrict your search, but initially we show everything that's available, which includes over 50,000 source tables. We call these source tables because they're the tables that come from our sources with minimal modifications on our part. That's distinct from our time series tables, which we have constructed ourselves. And then there's also a set of GIS files. These are available as shape files, providing boundaries, mostly boundaries, but other types of information too about census geographic units. Consider this map again. If you wanted to get the data to produce that, you could enter filters for block groups for the 5-year ACS period 2011 to 2015, and for educational attainment. And you can find that there are 17 source tables that cover this information. You could click on any of the underlined labels in this select data table to get more information. You will not see the actual data on this site, unlike data.census.gov. We provide only metadata and documentation. You will be able to download this information through our site. One unique feature is that you can sort all of this information by popularity. If you click on this, you'll get to see rise to the top the things that are most popular among our users, which is often a good way to find the table that you yourself are most likely to be interested in, given your filter selections. And that is the case here. This first table is the one that I think Kyle probably used to make that map. And to add it, in order to download it, you first add it to your data cart by clicking this plus sign. It works a lot like an e-commerce site, but instead of a shopping cart, we have a data cart. Up here, you can see what's currently in your data cart. I also want GIS files for my map, so I go to the GIS files tab and add the block group shapefile for the entire United States. And then I can continue to this page where I have various options for how to modify which source table information I'm downloading. Over here on the right, I can select extents, so I could restrict it to a particular state if I wanted to. Right now, the default is all extents in the US. I have the option to restrict it to particular breakdowns. Now, this is the geographic components that I think Noemi talked about just a little earlier in this session. You could basically restrict your information to some subcomponents of geography, not for block groups, but for higher levels. You could select other levels and add those to your cart as well, so that you could get the same table for different levels. And I just wanted to highlight too, going back to Noemi's talk, that she pointed out some summary levels that actually are parts where you have the state parts of places, or the place parts of different, the place parts that are in different counties and things like that. That is available through NHGIS as well if you show compound geographic levels. We call those, in NHGIS terminology, we call those compound geographic levels. And if you click on that, you'll see pop up down here a bunch of different compound levels that split American Indian, Alaska Native areas up by state, or combined statistical areas up by state, that sort of thing. Those are all available through NHGIS as well. Just proceeding through the end here, if you continue, there's several different structures that you can choose for your output data. And down here, you have the option to enter a description to describe your particular request. You'll see in a minute why that would be useful. You get to enter this yourself, and then once you submit your request, if you haven't already created an account with NHGIS, you'll be prompted to do that here. We ask you, when you enter that information, to agree to a couple terms: that you will cite us if you use our data in a publication, and that you won't redistribute our data without permission. And that generally applies to, if you grab a whole file and you want to just put it on your website and let people download it, we prefer you not do that because we need to keep track of how people are using our data in order to inform future grant applications. It's important for our funding model. So once you've agreed to those things, then you can proceed to your extracts history, where we keep track of every request that you've ever made with this account, so that you could return to those. And of course, here's where that description is valuable. You can see past requests that you've made, and your description will help you distinguish those if you ever want to go back and revise or resubmit. When you first make the request, what you'll see here is a spinning circle until your request is ready and ready to download as what we call a data extract. You can then click these buttons, tables, or GIS files to download your data, open them up, they're in zip files, and load them into whatever software you'd like to use to analyze. Here, this is ArcGIS Pro, but obviously there are other GIS software packages. You can also use libraries in R or Python, lots of different ways to analyze spatial data. All right, now I'm going to return back through what NHGIS has to offer generally, starting with our summary tables. We have summary data going all the way back to 1790 at the state and county level, sometimes at the nation level as well. Our census tract data goes back only to 1910. That was the first year that the Census Bureau produced census tract level data. And we also have all census levels down to blocks going back to 1970, which is the first year that the Census Bureau published what are today called summary files, actual large bulk digital data sets. There's a little bit of digital data for 1960, but it doesn't cover that many levels. So we've got all of that. One caveat with the tract data you should know is that it started small with only 8 cities in 1910, and then grew to cover more and more areas until 1990 when it did cover the whole nation. Other places on our website where you can get an overview of what's available. Key page for that is our data availability page, which gives a summary of all of our different types of data. If you zoom in on the summary table area, you can see we have a few things that aren't standard population and housing data. We have some county business patterns, vital stats, agricultural, religious, manufacturing data. These are mostly historical, not recent years. We also have a unique NHGIS product where we have taken land cover data from the NLCD and precipitation and temperature data and summarized that on census areas, counties, census tracts. We also just released last month new population and housing characteristics for 3 levels of watersheds. So we have both environmental data for census areas and census data for environmental areas. We also have annual census tract population estimates. If you're interested in any of those, just know that these special data types are available through separate web pages, not through the data finder. Another page that's handy here is our overview of NHGIS data sets. I will summarize all of our sources and for each of our main summary table types. We also have the original source documentation for most of our data, so you can learn more about that here. Next, GIS files. If you'd like to know what type of GIS data we have, you go back to that data availability page, click on the GIS files button or link, and you'll jump down to this table, and you'll see that we have all kinds of boundary data for recent years especially. I've highlighted these columns. These columns represent boundaries that we have derived almost directly from the Tiger Line files, but with some correction or some improvements, basically. We have, for one thing, in our version of the data, we add what we call a GIS join field, which is a standard identifier that is in all NHGIS data, all historical and contemporary data. It's always there, and it always has a G to start it, so that if there's a leading zero, it's preserved in whatever software package you open. You don't have to worry about the first zero disappearing in some packages and then having to re-add it in order to join things together. So it's in both our boundary files and our table files, makes things easier to join. We also have merged everything together into these nationwide files, and we clip out the coastal waters. I believe Kevin Hawley was yesterday talking about the different Tiger Line products and how Tiger generally extends out into coastal waters and in the Great Lakes. We have clipped those out so that you actually see the shape of the country that you typically expect to see. And that's somewhat involved. Here's Louisiana. It might not look like Louisiana, but when you add the water area, now it's probably more recognizable. We don't want all of this detail carved out of our boundaries, so we have taken the effort to identify what we consider to be coastal water, and sometimes that requires us, splitting up the Tiger water ourselves to figure out, what part is coastal and what part is not. Once we have that, we clip out our boundary files so that we have these. The caveat here, that's not always great because you might not want that much detail. We do not have generalized files like the census provides for recent years. All of our files have detail comparable to this, but at least then you will get the shape that you expect, and you will be able to do high precision spatial analysis with it. So that's recent stuff. We also have boundary files for historical data. What I started working on back in May 2001 was our census tract boundaries for historical census years. We still provide those. We also have newer versions of historical data. That includes place points going back to 1900. We do not have boundaries for places going back that far, but we do at least have points. So if you do have data that you get from, say, full count microdata that identifies all of these places, you will be able to georeference them to particular locations using these files. And here's an example of block level data going back to 1980. We haven't yet extended this series, but we could back to 1970 because we've also started adding 1970 block data. This is a big project that we've been working on for about the last 5-6 years of adding block level data, boundaries for 1980 and now also 1970. All of that information is available under our GIS tab here on our web page. We've got a GIS files page that provides documentation for all of this GIS work we've done. And then you'll see in this area of our page, there are sub-pages for 1980, 1970 block boundaries and place points. One other special type of GIS file, this one is available through our data finder. This is centers of population for states, counties, census tracts, and block groups. And this is data that the Census Bureau itself provides. There's a web page where you can go to get this information in CSVs. We have loaded that and created shape files. So we've taken just one extra step, not a difficult thing, but it's there and available for you to download this information in shape files. Yesterday, I believe Suzanne was demonstrating some maps that show where the state centers of population are. I think the centers of population for smaller areas like counties, tracts, and block groups are way underutilized. They can be really super handy for lots of uses, and I wanted to demonstrate one of those. Here's a proportional symbol map of population by county, California, Nevada. The default placement in a GIS is typically to just put that circle in the middle of the county. That gives you, in a sense, a misrepresentation of where the people are. Consider the same map using centers of population instead, and look at, I think they pronounce it Washoe County in Nevada, where Reno is located. Very long, north to south. However, most of the people don't live out in the desert. except maybe during Burning Man. The rest of the year, most people live in Reno, right? So the population center shows you that. And these circles put it right there. And that's true all over the place. Lots of movement here. These are big counties, and the population often doesn't live in the middle of those counties. What you can see, for example, is very clearly with these circles, you can see the Highway 99 corridor that connects all of the cities of the Central Valley very clearly here. That's, to me, is a great way to show this information at the county level. I'm getting a pretty good view of what the population distribution actually looks like. And you can do the same thing at the tract level. Here's the Bay Area of California. And again, like these circles put the people where they actually are. I'm mapping percent population under 18 years. I can do that at the tract level or the block group level. And I'm getting a really clear indication of where these people live. This technique is called bivariate proportional symbol maps. Bivariate because these circles represent both population with their sizes and a population characteristic with their colors, two variables. The typical strategy for showing this stuff, choropleth mapping, has some severe liabilities, in my opinion, compared to that technique, because it really emphasizes these big areas that may not contain anybody. Take, for example, these two census tracts. They're just as big, if not bigger, than San Francisco City itself. Should their information dominate the map as much as San Francisco does? These colors really stand out here. If you look at the proportional symbol map, the information for those two tracts is properly proportioned to the size of their populations. And because I'm using centers of population, I place those circles in the right place. So if you're interested in how I did this in ArcGIS or in other examples of why I think they're useful, I wrote a series of blog posts about it. You can do a search on bivariate proportional symbol maps or census centers of population and IPMs, and you should be able to find these blog posts. Moving on, what I have spent a lot of my research effort on since I started working on NHGIS is this problem of changing census boundaries. Small areas, especially census tracts and block groups, they change every 10 years, and they complicate our ability to measure change over time. Here's Charlotte census tracts in 1990 and 2020. If we zoom in on a couple areas here, you can see that the 1990 areas were much bigger than the 2020 areas. There's a good reason for that. The Census Bureau aims to keep tracts and block groups around the same population size across the whole country. That's useful, but it also requires that we split those things up a lot over time in areas where there's lots of population growth, which happened on the outskirts of Charlotte and a lot of other areas. But that's not the only kind of change. A lot of us are familiar with the Broomfield County quote unquote headache. If you're trying to measure change in counties, how exactly do we map Broomfield County's data to earlier county level data? Broomfield County didn't exist until 2001, I think, and then threw us all off. And of course, it's happened again now with the Connecticut County changes in the 2022 census, 2022 ACS data. The Census Bureau is now identifying planning regions instead of the historical counties for good reasons. But it obviously makes our life more difficult when we're trying to measure changes across time. And that applies not only to county level, but also to tract and block group level, where all of these codes are used in the block group and tract identifiers. That's not all. Geography is not the only thing that changes over time. In summary data, we also have changes in categories and concepts. The way they asked about education in the census changed between 1980 and 1990, and that changed the kinds of categories that are reported in these data. We have dealt with both of these issues to a large extent with our time series tables product. This is our time series tables documentation page, where we describe the different integration methods we've used, both for geography and attributes. So that means matching up those educational attainment concepts across time. You actually, as we saw, you access these tables through our data finder. One important column that I really draw your attention to here, I don't have time to go through all the details of our time series tables, but we have two different ways of doing geographic integration, and they're really importantly different. So you should be careful about which one you're getting. We use either nominal integration or geographic standardization. This table is an example of a nominally integrated time series table. And what we mean by that is we've matched up the geographies only by name across time. This is a state level file. That's, each row represents a state at different points in time across the columns. We matched these rows up across time just by state name. And that works really well because state boundaries really haven't changed in any significant way for many, many years. This, however, is an anomaly integrated census tract table. And you can see in this case, there's a lot of blank cells. That's because these tract numbers change across time. They don't exist in every census. And a particular row is only going to contain data for the census years when that tract existed. That's not all that useful necessarily for measuring changes within these tracts. Why would you want to do that? Well, if you wanted to create these two maps that I showed you earlier, you can do that with nominally integrated time series tables. But chances are you'd prefer to have data for consistent static units across time. And that's what our standardized time series tables do. Here's an example of standardized tract data, 1990, 2000, and 2010, where we have standardized the tract units to be the 2010 tracts. For 1990 and 2000, we have estimates of the characteristics for those 2010 tracts. And because they're estimates, we also have lower and upper bounds. Where did those bounds come from? Well, let me dig in a little deeper. Where our estimates come from is block level data. So in this case, for the 1990 data for the 2010 tracts, we used 1990 blocks, which are in the pale red here. Good news is, for 5 of these tracts, those 1990 blocks nest perfectly within the 2010 tracts. So we can just sum them up to get the correct data for those 2010 tracts. Over here on the west side of this example, there's 3 1990 blocks that are split by the 2010 tract boundary. So we don't know exactly where those people lived. We have a model. I won't go into detail on it, but we estimate that 201 people lived on the north side of that boundary, 14 on the south side. What if everybody lived above? That gives us the upper bound for the northern tract. What if everybody lived to the south? That gives us the lower bound for the northern tract. We provide that information to give you a sense of how reliable and how much uncertainty there is in these estimates. Our standardized time series currently go 1990 through 2020 censuses for 2010 census units. Here's an example at the block group level for Detroit. We provide that for 10 different geographic levels listed here. There are about 1,600 standardized time series in 115 tables, but that's covering only short form census data. The short form is the form that goes out to everybody in the historical censuses, 1990, 2000, and then starting in 2010, it's the only thing that goes out in the decennial censuses because the ACS started covering the information that used to be covered in a long form sample that was part of the census. The short form covers these subjects, and it's the only information that's available at the block level. And that's why our time series are restricted to that, because currently the standardized time series are based on block level data only. So we don't include things that are in the long form or the ACFs. The nominally integrated time series do include that long form information and the ACS information. So there's a lot more tables, a lot more time series covering all of those subjects, just 8 geographic levels. They go a little bit farther back in time because they're not restricted to the block level data. And they also include 15 ACS 5-year periods going back to the 2010 5-year. What if you do want to standardize long-form data or ACS data? Then you can go to our geographic crosswalks page and access those crosswalks. These are like the relationship files that the Census Bureau provides. However, we include interpolation weights that allow you to that are intended to be used for allocations from one year's boundaries to another year's boundaries. And they're based on models that help you do that sensibly. We have a lot of different crosswalks now for lots of different time spans, from 1990 to the 2010s, 2000 to the 2010s, 2020s to 2010s, and the other way around. We're also working right now, I think in a few weeks, we'll have new crosswalks out for 2000 to the 2020s. Why do we use a plural here, 2010s and 2020s? Because we also have crosswalks for specific years in the 2010s and 2020s. These are years when there were some substantial changes in block groups, census tracts, or counties in ACS data. So for example, in 2022, as we talked about, the counties change in Connecticut. Here's two maps of change in percent work from home, one for 2010 Connecticut counties and one for 2022 planning regions. And you can create either one of these with our crosswalks. We have a lot of different target zones, so you can create standardized data at any of these levels. You have to start with block data for these levels, but for block groups, census tracts, and counties, you can start with blocks, block group parts, or block groups, or census tracts. Let me explain. How to estimate 1990 characteristics of 2010 tracts. Ideally, you'd start with blocks. As I demonstrated before, those nest well within 2010 tracts. But we don't have long-form data for blocks. So you could start with tract data instead. That's kind of the intuitive thing. A lot of people think, I want to standardize tract data, I'll get a tract-to-tract crosswalk or relationship file. However, as we've seen, it's better to start from smaller units. And there are smaller units with long-form data, including block groups, and for the 1990 and 2000 census, block group parts, which were the intersections between block groups, places, county subdivisions, and other areas. These are the smallest units you can get long-form data for, so they are the best units to start from for standardizing across time. How much difference does that make? You could start with a tract basis, but then you kind of end up assuming a uniform distribution within each tract. The block basis shows there wasn't uniformity within these source tracts. So you can't use a block basis for long-form data. You could use one of these, and you can see that as you get smaller and smaller, you get closer to the block basis. We've done some work in the Federal Statistical Research Data Centers to assess these things. And what I want to point out here is we actually have taken 2000 and 1990 census responses, the complete set within the RDC, and we have geolocated all of those through a sophisticated model, bringing in all kinds of information in a geocoder. That information, I won't go into the details of our results and findings, but that information is also available for researchers working within the FSRDC to get specific locations for 1990 and 2000 census data. And that product is called OSCILAT, Optimized Spatial Census Information Linked Across Time. Look it up. If you're working with an FSRDC, you can find that. Here's a list of some of the interpolation weights available in our crosswalks. All right. I have left myself very little time to get through IPUMS USA, and that's more or less okay, because as I mentioned earlier, we don't have as much geographic detail in the microdata, but we do provide a lot of resources for working with geography in the microdata. In IPUMS USA, we have US decennial census samples. We have American Community Survey data. We have full count microdata. That's everybody who was in the census for years 1950 and earlier, because there's a 72-year limit on the privacy of census information. So now we can actually provide all of this information 1950 and earlier. For the more recent years, we have this restricted geographic detail. The public use microdata samples, or PUMs, include regions, divisions, states, and public use microdata areas, or PUMAs. Those have to include at least 100,000 residents. So they average around 135,000 people. There were similar units back in 1970 and 80, and IPUMs, we have created 1960 pumas and mini pumas for 1960. Here's an example of what those pumas look like. The blue lines represent the puma boundaries. They don't always correspond perfectly with counties or with metro areas. They vary a lot in size. They're smaller, within urban areas, much bigger in rural areas. So what can we do to help with this? We try with IPUMs USA to identify counties, cities, and metro areas wherever they match up well with pumas. So for example, you could take West Valley City, Utah, has one puma that has a majority of its population in that city. So that's its best matching puma. We figure out how many people live in the city but not in the puma, how many people live in the puma but not in the city, and we add those two percentages up, and that comes up to 3.89. And we will identify any city where that sum is less than 10% for cities. We do the same thing with metro areas up to 15%. And that's available through IPUMs USA. We also provide metro status and percent metropolitan. Here's an example of the metro status of each of these pumas. You'll see there's a lot of things that are orange of mixed metropolitan status. So you might prefer to use percent metro, which allows you to say, if you wanted to just divide into two classes of metro or non-metro, you could just use the breakpoint of 50%. But there's a lot more going on inside of pumas. So you might also want to get information about like the density within pumas. So we also provide that as a statistic. You can get the population weighted average tract density within each puma. You can get the average micro area population for each puma. And then you can combine these things together to get different dimensions of urban and rural settlement. So high density, high metropolitan population, those are centers of metro areas, where you can distinguish the centers of mid-sized metros, suburbs or exurbs, or rural non-metro. You can distinguish all of this with these variables in microdata. And then you could compare that to other features like poverty rate. One other thing we do is cons pumas. Pumas change every 10 years, like tracts and block groups do. So here's the 2010 pumas in New Hampshire. Here's the 2020 pumas in New Hampshire. There were 10 in each of those years, but their boundaries changed. We provide a variable called cons puma that provides the areas that aggregate up to a consistent footprint with some give for small changes. Like this one little area is in a different 2010 and 2020 puma. So we allow for that in our cons puma definition so that we don't have to aggregate too much, up to a 1% tolerance. You can find all these geographic tools and resources on this page of IPUMs USA. If you want to learn more about other resources we have or go into more detail on this, we recently gave a webinar, which you can access through the ipums.org page through the support tutorials menu option. And jumping ahead very quickly, you should know that with the full count microdata, the historical stuff, you can get exceptional detail. The trick is that it hasn't been georeferenced yet. It's not all in a GIS, right? We don't know where all of these historical entities are located in a GIS. You can get state, county, and city. You can get enumeration district, which is kind of similar size to block groups. You can get these maps online, but they're just map scans. There's a few groups who have worked on creating ED boundaries, and we've got a grant application in right now to add those ourselves, but it's not all there yet. In the restricted access full count microdata, we're not allowed to share this publicly because we work with Ancestry.com and other commercial entities who want to provide this for genealogical purposes. We have full names and we have addresses and minor civil divisions. These are available through approved researchers for approved research projects. Lastly, I won't go into a lot of detail here, but NHGIS, IPUMS, we have an API similar to the Census API. It allows you to access our extract system to make data requests and download data. And with NHGIS, you can also query our metadata. Here's the API page. We have an IPUMS R package. We have IPUMS Python package. And those are all accessible through the NHGIS webpage here. All right, I'm probably a little past time, but thanks for sticking with me. I want to acknowledge our funders and share this information about ways you can contact us if you have more questions. All right, I will stop sharing.
Wow, thanks so much. That was really informative. A lot of great information there. And one person expressed the sentiment, and I agree. Many of us at Census agree. Not a question, but a comment. NHGIS is the most awesome website in the history of the internet. So you have a lot of fans on here today.
Wow, that's
So basically, one question people had, I know you standardize, you said mostly on 2010. Are there any plans of standardization using 2020 units? And if so, will that be coming out anytime?
Yeah, not all the way soon, but I mentioned that we are working right now on crosswalks from 2000 to the 2020s. Our next step is crosswalks from 1990 to the 2020s. Once both of those are done, then I expect we'll be working on time series tables that are standardized to probably 2022 geography. So we'll go right through to the present Connecticut planning regions.
Yep, that makes sense. Great. Thank you so much for joining us. I really appreciate it. Our last session of a great conference, and thanks again for joining us, will be Glenn Rice. Glenn is the director of the MCDC, the State Data Center for Missouri, and he'll be talking about GeoCore. Thanks so much for joining us, Glenn.
Okay. Hi, my name is Glenn Rice. I've been running the Missouri Census Data Center for about 10 years. Today I'm going to be talking about GeoCore, a application that we host on our MCDC website, and give you some examples of how it works. I should say I didn't invent this. I'm responsible for its maintenance and updates, and I'll list some full credits at the end of my presentation. By the way, this is the last presentation of this GeoForum, and I'm finding out a major disadvantage of going last is that all the other presenters, many of the other presenters, have brought up topics that I would have loved to have worked into my presentation and responded to directly with some of the ways GeoCore could help with that. Unfortunately, I just didn't have time. So also some of the questions and answers in the Q&A. At any rate, let's talk a little bit about what GeoCore is and what it can do for you. Basically, GeoCore stands for Geographic Correspondence Engine, and it's a web app that generates files that we call correlation lists. And this enables us to look at relationships between different geographic coverages in the United States. Now, in other words for these are things like crosswalks, correspondence files, that sort of thing. These lists can be used to reallocate data between different types of between different types of geographies. Why would this be useful? Well, I mean, people have used these sorts of lists for all kinds of uses, but a really simple example is if you have data from survey or some other instrument that's been aggregated by one type of geography, but you're going to be reporting or analyzing these results using a different type of geography. So an example that we're going to look at today during this presentation is moving or reallocating data that's been recorded or aggregated at the zip code level into congressional districts for one or more states. Here's the example we're going to look at. Excuse me. This is from an article from the Center for American Progress website. This organization, nonprofit, has been using GeoCore for a number of data analysis, and I'm giving them thanks here for letting me use this article. The article is about the Consumer Financial Protection Bureau, which is I'm not sure whether they're a government office or what, but they process consumer complaints about the financial industry and financial businesses. And at any rate, we're going to look at reallocating complaint data from the CFPB into from zip codes into congressional districts. And we'll return to this example in a minute. But first, let's take a little look at how GeoCore works. I'm not going to read every single geography on this slide, but we have many different types of geography in GeoCore, including administrative areas, statistical areas, census areas, urban, rural, legislative, and then a mixed bag of other areas, including some that aren't listed here. Some of these geography types are updated every 10 years. The census areas, for instance, some more frequently. For instance, state legislative districts may change every 2 years depending on your state. They don't always. School districts do change frequently, but usually not on any particular schedule. We will add new geographies if they're substantially changed or, as they become available. Also, I'm going to say right now that for the purposes of this presentation, I'm going to use the terms zip code and ZICTA interchangeably. And also, when I say county, I also include county equivalents. GeoCore works with a couple of assumptions. For one thing, we assume that all geography types have non-overlapping coverage. Okay, so for instance, counties, a person can only exist in one county at a time. Same with congressional districts. They completely cover every state with no overlaps. They also have no gaps, but we do allow for geography types that have gaps. For instance, ZICTAs, CBSAs, census places, other areas like that. The final assumption is that all geographic units can be defined in terms of census blocks. Okay, so the block is the smallest unit of GeoCore. For every block we have in the database, we know only the total population, the area, and what it is part of. Okay, so for any given block, we know it's part of, such and such a county, state, and other entities. The correlation list is what GeoCore produces. I mentioned this early on, also called equivalency files or crosswalks, correspondences, whatever you call them. It's basically they're a way to describe relationships between geographic entities. The key items on any correlation list are going to be a unique ID or name of the sources and the target geographies. And for each intersection of these things, we will have an allocation factor. And the allocation factor shows what portion of the source area is within the target area. Another element of correlation list is often the size of the intersection, usually included. It's not essential. We'll see it in some of my demonstrations here. The size of the intersection is usually defined in terms of some variable, typically population. All right, so looking at each of these in turn, source geography is going to be the starting point for any correlation that you might be wanting to do in GeoCore. This is your source data geography type. So in the example we used before, the Consumer Financial Protection Bureau reports de-identified consumer complaints, at the state and zip code level. So the source geography here is zip codes. By the way, this is a greatly simplified, the screenshot of this spreadsheet, greatly simplified. I took the list that I got from the CFPB and aggregated by zip code using SAS. And that's what you're seeing here. Target geography is what you're desired, is what you want out of the correlation. So in our example, again, the journalists are writing an article about the consumer complaints, but they want to put it in the context of congressional districts. So the target geography where the desired data is your congressional districts. Intersections are a key concept in GeoCore. The intersection is the overlap between one source and one target. There's different ways things can intersect. One can be completely enclosed by the other. There can be partial overlaps. And we can describe intersections as collections of blocks that exist in both geographies. That's because of our geographic assumption that all units in GeoCores are made of complete census blocks. So, and then the size that I mentioned earlier is going to be the total population added together of the block, or whatever you're using as your size variable of the blocks within the intersection. GeoCore has an option to use land area for the size of the intersection, as well as housing units. In most cases, if you're doing demographic or social research, you're going to want to use population, simply because, you know, the people are what's important. To further illustrate what we're talking about when I talk about intersections, is an example here from my home state of Missouri. There's a city called Cameron that covers portions of DeKalb and Clinton counties. So this combination represents 4 distinct intersections in the relationship. Area 1 is where the city limits of Cameron and DeKalb County overlap. Area 2 is where the city of Cameron and Clinton County overlap. And 3 is the part of DeKalb County that is outside of the city limits of Cameron. And likewise, 4 is the portion of Clinton County that is outside of the city of Cameron. Technically, areas 3 and 4 are not really intersections because there's only one element to them. But it's useful to think of them as intersections, and we'll see why here in a minute. Okay, I'm going to spend a little time on this slide because the allocation factor is the most important part of understanding and using GeoCore. The allocation factor represents that portion of a source unit that exists within a single intersection with a target unit. So another way to think about that is that a single source unit may intersect one or more targets. The allocation factor shows the size of each of these intersections relative to the source. So the allocation factor is the magic number that will enable us to transform sources into targets. Let's look at the example here, this table. I hope everyone can read it. This is using the example from the previous slide here that we just looked at, Cameron and DeKalb counties. So the total population of Cameron is 8,513. That number becomes the denominator for all of the allocation factors shown here. So the first row of the table here corresponds to the intersection number 1 on the previous slide, that part of Cameron that overlaps DeKalb County. The size of that intersection in population is 3,360, which divided by 8,513 yields an allocation factor of 0.39. So what that means in plain language is that 39% of Cameron's population is in DeKalb County. Well, presumably, using our algorithm here. And then the same thing holds down here. This corresponds to area 2 of the previous slide, and it indicates that 0.61 or 61% of Cameron's population is in Clinton County. We call this allocation factor AFACT, just for short. We can and GeoCore gets all of these numbers by simply adding up the population of the blocks in the intersection. We can also get a second allocation factor, and what we call the inverse or AFACT2, and that shows the opposite direction. It shows the ratio of the intersection to the target geography. In this example, 0.3 or 30% of DeKalb County's population is in Cameron, and 24% of Clinton County's population is in Cameron. These correspond to intersections 3 and 4 in the previous slide. So these two. Now notice that the allocation, the primary allocation factors will always add up to 1. However, the inverse of that is not going to be true. Okay, a fact 2 is not going to add up to 1 because in this case, well, with the allocation factor, we're talking about the same fractions of the same unit, which is Cameron, Missouri. Whereas if we can't add these up because they're talking about portions of different units, in this case, 2 different counties. So that's why it's irrelevant to like add these up. Another example is that sometimes we have geographies that don't have complete coverage. In those cases, we will assign a special target unit, often coded as all 9s, to show areas that are not in whatever the source unit is. So, for instance, here's a fairly contrived example. Most counties have more than just 2 places, but I found a county in Nevada that has only 2 places. Crescent Valley, Eureka County, Nevada only has 2 places. So what the allocation factors show is that about 27, but close to 28% of Eureka County population is in the town of Crescent Valley, and probably a CDP actually. And about 22% of Eureka County's population is in Eureka, Nevada, and the rest of it, or just over 50%, is outside of any place. And that's what this means by not in any place with this special place code. Let's put it together here. Back to using our example of the consumer complaints. We have them already aggregated to zip codes. So zip codes is our source. We want the data aggregated to 1/19 CDs. So that's our target. And then we need to figure out how to divvy up. So we need to reallocate these complaints from each zip code into the CDs that cover it. So that's where the allocation factors come in. And then will also be a little bit of post-processing required. Onward to GeoCore. We have multiple versions, at least one for every decade since 1990. And you'll want to use the one that's made for whatever decade you're looking at. In this case, we're going to be using recent data and geography. So we're going to use the most recent version, which is GeoCore 2022. And note that these years, they don't represent like data years or anything. That's just the year that it's a convenience. It's just a version number. There's the link. It'll be in the slides when you get them after the presentation. Here is just a screenshot, and I'm going to do some live examples here in a minute, but this is a screenshot of how the front form of input form of GeoCore. And so normally you'll like select one or more states, and then you select your source and target. So also I've got some links up at the top that might be useful, help and examples, but normally when I do a GeoCore run, I will start with just a single state. And I'll explain further why in a minute, but basically it's to test if my query is working right. And usually I pick Delaware just because it's a small state, it's near the top of the alphabet, so I don't have to scroll very far. And just, I'm like a previous presenter, I just love Delaware for this kind of stuff. And then you'll want to choose your source and target geographies. In this example, we're going with ZIP or ZICTA, and then we're choosing the 119th Congress for the target. There are a couple other options that are going to be useful here. Normally, CSV output is selected by default. There's another option for under that dropdown, not shown, for tab separated values. And then there's one for generating a web page report. I usually find that it's easy or helpful to test the results using the web page report option. And then when you go to your full-on analysis with many, many states, turn it off. The reason for doing that is the HTML output option is very slow, or can be on the server, especially if you're running a lot of states. The CSV output is super fast, but the HTML output with many states can actually cause server timeouts. So that's why I tend to use it just for testing, and then turn it off when I want to actually do the real work. One other option that might be useful if you're working on small areas, GeoCore normally outputs an entire state or multiple states worth of data. If you're just working at like a county level or a few counties, you can go down to this section of the form and put in FIPS codes of 3 different kinds. You can put in county codes, 5-digit or 3-digit county codes, CBSA codes that are also 5 digits, I believe, and place codes. Well, it's 7 digits with the state. Anyway, these are all FIPS codes you can enter in here, and it'll filter by that in the results and make your results a little more manageable if you're working in smaller areas. Once you click enter or run, or I don't know, whatever it is, your output's going to look like this. It doesn't look like much. It's mostly technical details, but it does show a few things of use. So it shows your states that you're processing, source and target geography, how many census blocks were picked up by your selections. So it looks like we got them all, 15,317 blocks, excuse me, in Delaware. It's got links to your 2 different, in this case, 2 different output files, and how many observations are going to be on the list. This is what the web page results look like. And again, we'll be looking at live examples here in a minute. This is the example that I just ran with Delaware, just the first 2 lines. So these are the first 2 zip codes or ZICTAs in Delaware. And it shows that both of them are in Congressional District 0, Delaware District 0. And it shows their population and allocation factor, which in both cases here is 1, which means that both of these ZICTAs are completely, all of the ZICTA is part of this congressional district. If the output you get looks good, you can go back to this form, click the back button, and change your inputs to whatever you like, and turn off the HTML output, select all your states, and go ahead and submit your final run. Or you can go back and tweak it and work on it a little bit more. Point is, you just use the browser's back button to go back to the form. This is the CSV results, and this is the sort of the meat and potatoes of the GeoCore output. I've done a little bit of reformatting here for the purposes of this demonstration, but it's going to look a lot like this. So this is, again, using this example of ZICTAs allocated to 1/19th Congress districts. So each row in this output represents an intersection between a source and a target geography. So the results are normally sorted by the source geography first. So in this case, ZICTAs, and then the target geography codes. In this case, 1/19th Congress. Now, for a lot of places, state will be automatically included especially for entities that don't have unique numbering between states. So, for instance, many states probably have a District 3. So in that case, we also include the state code with it, so you can uniquely identify these later. Note here also that the Pop 20 column shows the size of the intersection only. So for each line, it shows the size of that intersection. So for instance, on this first line, it's the size of the intersection between ZICTA 65201 and State Congressional District Missouri 3. It says total population, and sometimes that can be a little confusing, but all you need to do is remember that each row is an intersection. So here, these first 2 highlighted rows show my own zip code, 65203, where I'm talking to you from. My city, Columbia, Missouri, and my zip code are both split between Missouri districts 3 and 4. We can see this in the AFACT column over here, that here's my zip, here's Congressional District 3 and 4, and you can see from the AFACT that 8.8356, or about 83.5%, of the population of 65203 is in District 3, and the remainder, or about 16.5%, is in District 4. Down here on the green line, it shows a zip code that's entirely in District 3, and that's indicated by the allocation factor being 1. So zip 65233, I think, hard to read, is entirely within District 3. And similarly, further down here, the orange rows show a zip code that actually falls within 3 congressional districts, Missouri 3, 4, and 6. It looks like from the allocation factors that less than 1% of this zip code is in District 3. The majority, at about 82%, is in District 4, and the remainder is in District 6. So what we can do with this correlation list is now build out our results. So you're going to have to do some post-processing with this. The final step is to combine the source data with the zip code. The source data by zip code with the crosswalk or correlation list that we just created. I'm showing you this example using spreadsheets, mainly just for illustration. It's possible to do this in Excel, but you'll hate it. Most users are going to prefer software like SAS, maybe SQL or Python, or just whatever analytical tool you prefer, just because you're going to have to do a lot of sort of combining and aggregating. So the first thing I did was I combined state with congressional district code. So we basically now have a unique code for every congressional district in the country. 12, I believe, is Florida. So yeah, these are all Florida congressional districts. Down here, well, it shows that the count of each source geography gets multiplied with the allocation factor of the intersection to get the count for the target geography. I'm also rounding here, so we don't have like a fraction of a complaint. So basically, I just round to the nearest whole number for this. If the allocation factor is 1, so let's look at the yellow row up here. This allocation factor is 1, which means that all of the source areas count gets allocated to a single target area. So in this example, all 30 of these complaints get allocated from zip code 33101 to Florida 27. Okay. If the allocation factor is less than 1, the source areas units or complaints, in this case, are split between the 2 or more target areas. So, for example, in the green row, this zip code 33125, it's got 3,007 complaints overall, and they get split by this AFACT into 1,107 in District 26 and 1,900 in District 27. And likewise down here, the blue rows, this single zip code 33136 with 1,074 complaints overall in the whole zip code gets allocated 3 ways to districts 24, 26, and 27 according to these allocation factors. So that gets multiplied out, and these are the allocated complaints. So what you then need to do is go ahead and bring these over and put them together by district. Okay, so we put all the 27s together, we put all the 26s and 24s, and likewise for all the other congressional districts. And then eventually you're going to have these numbers over here, which is the total for each district. That is the outcome that you're after. The the file that you get out of this can then be joined to a GIS or a layer file or any sort of mapping software to produce a map, or you can do further analysis. But that is the final outcome of the process of GeoCore in a very short demonstration explanation. Speaking of demonstrations, let's do a couple now. Okay. Yeah. First thing before I get into the demos is this is the front page of GeoCore. One thing that might be useful when you're doing this, if you're confused about some of the geographies, is the geographic glossary. This is basically goes into a lot of detail about all of these geographies and some of the gotchas and some of the weird things about a lot of these things. So jumping right in, excuse me. Earlier, a presenter was talking about urban and rural. We do have census urban and rural designations. These are done at the block level. So what we can get out of this is the percent of urban and rural for pretty much any geography type that exists in GeoCore. So what I've done here, I'm looking at starting by looking at Arizona, and let's look at this example. I'm going to look at the rural and urban portions of the 119th congressional district. So this is my source geography, and then down here, where is it? Did I already select it? Yeah, there it is. Urban rural portion. I'm going to leave everything else the same, and I'm going to do the HTML report. So go ahead and run request. Here is the query output page that I mentioned before. I did not choose CSV, so that link is not there. Click on that, and it'll bring up a new window or a new tab. Excuse me. With the listing of geographic correlations. So this is the web version, and like I said, it's probably not very useful for analytic purposes because you can't really, I guess you can select it and copy it into something, but it's really more for testing to see if it works. And I'll be using this for all our examples here. This results show that of the Arizona District 1, about 0.227 or only about 2% is rural. The vast majority is urban. This is pretty simple stuff. You can do this with any other sort of geography that we have here. It's a really simple way to kind of get urban rural for any type of geography that we have here, including there's quite a few. Another example of that, let's look at just one other example of doing urban rural. I'm looking here at 2023 CBSAs. Oh, and while I'm in here, I might as well show you how some of these geographies are organized. The 2020s are going to be mostly the census and statistical, or I'm sorry, the census tabulation geographies that are changed only once every 10 years. For other that change more often, usually they'll be grouped according to whatever year vintage they are. Congressional districts get their own section here. And then I've got a bunch of other geographies, including a few that relate only to Missouri, because that's where we get our money. So I'm looking at right now. I'm going to look at core-based statistical areas, and again, I'm just going to check on urban and rural portions. And I'm just doing this one to just show something that probably most of you already know, is that whether something is part of a CBSA or not doesn't really have a whole lot to do with how urban it is. That's frequently used as a proxy. I don't think it really should be, but you can look at, for instance, there's a CBSA, Nogales, Arizona, that is about 60%. It's about 60% rural. I believe there's a famous example about the Grand Canyon being actually considered urban by CBSA standards. That's pretty interesting. Okay, change over time. Because we have multiple vintages of certain geographies, you can use GeoCore to help work with longitudinal data, or to sometimes if you need to describe change over time. So for instance, congressional districts, they change sometimes every 2 years, but sometimes not. For example, between the 118th and the 119th Congress, 5 states changed their maps. And I don't remember off the top of my head what all they are, but I know one of them is New York because I've got it pre-selected here for my example. So New York, we're going to go from 118th to 119th Congress and just take a look at that. And I will also do some of these other optional inputs on a different demo. Okay, so here's our results. So what we can see here is that it's true. In New York, many of the 118th congressional districts did change when they went into the 119th. Some by not very much. In fact, this 52 might even be an artifact of the way this was done, or might have even been just like one block. I mean, this can probably be ignored. But some districts like District 4, New York 4, were unchanged between the 118th and the 119th, and that's indicated by the allocation factor of 1. They're congruent. Some of them changed just a little bit. You can see that CD 6, most of it stayed where it was, but some of it, about 48,000 people moved into District 14, or about 6%. So this is the kind of example of the kind of thing that you can do using the same geography but different years. GeoCore can also produce a few other outputs besides correlation list. Okay, a correlation list is the primary output and the primary use of GeoCore, but it can produce several other things, which I'll show you right now. One of them is just basic population counts. This is really useful for things that you can't really go to data.census.gov for a quick count on. I'm using an example, and now you might be able to do that on the census site, but the example I'm going to use here is school districts in Missouri. And if you do it if you want to just get population counts without a correlation, you can just use entire universe as your source geography. The entire universe actually is the whole US, but yeah, well, so let's run that request, take a look at the results, and we can see that we don't have we do get an allocation factor. It's a little more complicated here because we're using the whole universe, which says in this column US, but that's sort of a misnomer because we also filtered it by state. So we're looking only at the state of Missouri. So this allocation factor shows the portion of the state's population that is well, the portion of this entire list basically that is represented by this district. So this is a useful way to get codes and names and also total populations. Another thing we can do with GeoCore that doesn't involve correlation list is weighted centroids. I'm going to put up a page here. This was a journal article from a few years ago, 2022. Excuse me. The journal Health Affairs, they published this article about spatial access to hospital services for minorities. The authors used GeoCore to calculate distances between the population weighted centroids of ZICTAs and the location of the nearest acute care hospitals. So they didn't need a correlation list for this. All they needed was to get population weighted centroids. Now, what population weighting does is that it takes the blocks. We have the centroid location of the centroid of each block, and it weights each centroid by the total population of the block, and then it takes the average of those weighted locations, and that becomes the population center, essentially the population center of whatever your source geography is. So here's an example, that exact example. We're going to use Georgia for this. So in that case, we're going to go with zip and entire universe, since we're not looking for a allocation factor. But here's a new option that we haven't used before, and that is to calculate the weighted centroids. By the way, on most of these, you can click on this and it'll take you to a help page that gives greater detail. So in this case, we're going to do the calculate weighted centroids, and here we go. So just looking at this, you can see it gives the zip codes or ZICTAs, what they're named, the total population of each, and this is weird. This is weird. Okay, yeah, the total population of each, and the weighted centroid based on the population. Okay, this centroid is the average of all the centroids of the blocks that are part of the ZICTA, weighted individually by the block population. So it functions essentially as a population center. If you do it, I'm going to show you a very similar example here, again using Georgia ZICTAs, entire universe, calculate weighted centroids, but this time I'm going to change the weighting variable. Okay, remember, I believe earlier I said something about we can use the weighting variable is what's used to represent the size of each intersection. So in this case, I'm going to switch it to housing units. Let's run that request, take a look. Okay, so this is the same list as before, except for one key difference. Whereas the earlier list uses population as the weighting factor, this one will use housing units. So let's say the study was not about characteristics of people, but about characteristics of housing in relation to hospital locations. Okay, that's sort of a weird, maybe that's a contrived example, but I'm sure there are plenty of examples of where you would want to use housing units. So in this case, the weighted centroid that you get back is going to be what amounts to like a housing center or something for each ZICTA, if that makes sense. Yeah. Another option we can do here, and I'll try to wrap this up fairly quickly. I know I'm going really fast, but I'm short on time. We have one other set of options that I did not look at in the slides, and this is point and distance options. So let's say we need to know the population that lives within a population within a certain distance from a central point. And also, say you also want to know what part of that population lives in what cities or towns. This type of analysis, you might be very useful if you're trying to locate, find a new location for your business, or also for industry, perhaps with emissions compliance or that sort of thing. You want to know how many people live in a certain area and where they live within that area. So the way I would do this in GeoCore, using this example. So I'm going to use the example of the city of Washington, Missouri. So I'm using Missouri. I want to select the places within my area and the entire universe, because again, I'm not needing an allocation here. But down here at the bottom, I've already I've figured out where the location is that I want. I already looked up these coordinates. So this is the center point, 3855 north, 91 degrees west. And I'm going to use a 20-mile circle around Washington, Missouri. So you can add your own label here. Okay, so here are the results. The population. So in this also, we have a new little caveat here, or explanation here of what we're looking at. And this basically shows that it looks like there's, I don't know, what about 30, maybe 30 towns within 20 miles. So again, if you do point and distance, it will calculate the weighted centroid, and it uses that for the distance calculation. So that this distance is the distance from the center point that I specified within 20 miles of this point. So these show, and again, this is a type of intersection. So this shows the portion of Augusta town that is within, well, this number shows the intersection of the town of Augusta, Missouri, and a 20-mile circle centered on Washington, Missouri. Very interesting, and you can dig deeper and add other levels. One other thing I want to point out about this result is, remember how I said that there is a special geography that means not in a geography? That's this one, and it means that of all the people in that 20-mile circle, about 73,000 are not in any place at all. Really, a plurality for sure. I don't know if I have time for the rest of my. There are a couple of. I will go real quick through these. GeoCore also includes a number of artificial geographies or pseudo geographies. These are basically here for for convenience. So, for instance, an example of that might be what we call the best school district. So, some states have more than one kind of school district, and instead of having to run a separate correlation for unified or elementary, you can do best school district. And if you do that, I usually choose best type. I'm going to take a look at that for Connecticut. And the results there basically show it's complete coverage. So these are all every place, at least complete coverage that has a school district of any kind. And it shows which kind it picked up. E is for elementary, and U is for unified. So between those things, you'll get all the school districts that cover non-overlapping school districts that cover whatever state you've chosen. In this case, Connecticut. One final example I'm going to do of a pseudo geography is CBSAs. This indicates we've got a couple of special geographies here called CBSA type. Okay, as most of you know, CBSA can be either metropolitan or micropolitan statistical areas. So selecting this as a geography type will get you which one it is. And another one that might be useful is central county of the CBSA. And I'm going to go ahead and pick that up with county. Now, I will point out here that when two geographies are similarly sized, the output's going to make more sense if we put them together on the same side, okay, source or target. And you'll see why in a moment, but if they're the same size item, it's going to make a lot more sense when you see the results. Let's go ahead and take a look at that. And so here's an example of what that output will look like. Again, we're using Georgia as an example here. So the first row shows the CBSA number 10500. It shows that it's a metro type. Now, I could have put CBSA type on the other side of this, but it would have made just as much sense. It would have been a column that had all metros in it, so not as useful. That's why I was talking about earlier about uh, geographies of comparable size should go on the same side of a correlation or a correspondence. Over here, you can see that one of the options for the target is whether it's a central county of a CBSA. In this case, we can see that the CBSA is a metro statistical area, Albany, Georgia, comprising 4 counties in Georgia, Doherty, Lee, Terrell, and Worth. And of those, Doherty and Lee are both central counties, and Terrell and Worth are outlying counties of the CBSA. One other thing I'll point out very quickly on this is, where is it? Oh, take a look at this CBSA. This one is actually crossing a state line into South Carolina. This is kind of a gotcha that you need to watch out for, because on the form, I chose only Georgia and not South Carolina. This listing is only going to include Georgia counties, which also means that these allocation factors are probably not accurate because the CBSA includes some counties that are not shown here. You notice all of these are in Georgia. It's not including any of the counties in the CBSA that are also in South Carolina. So you got to be careful about that kind of thing, especially, well, always with any geography that can cross state lines, which is a lot of them, surprisingly, including ZICTAs. That's it for the. I'm going to go to demos. Am I back on my? Yeah, back on my demos. I'm going to finish up my presentation here, so bear with me a moment. GeoCore's limitations. Well, I'm going to spend a little time on this, and the major limitation is that in every version of GeoCore, all geography types are defined in terms of the single census block. Okay, and each census blocks, as everyone knows, we get redefined every decennial census. So the result is GeoCore can only compare geographies within the same decade. There are going to be a few exceptions. We do have some UMAs that have been redefined, but in general, you can only do crosswalks between geographies of a similar vintage within the same decade. I know Jonathan and his group have been working a lot towards making cross-decade correlations possible. It's great work, and we're not trying to replicate that here. This is why we have multiple versions of GeoCore, one for every decade. We could come up with an artificial unit. Well, we really can't use an artificial unit like a grid because populations change all the time. It's not practical for what we're doing here. The other main limitation is that it makes an assumption. I think other presenters have touched on this, that all subpopulations are spatially distributed the same way as the total. That's rarely the case, especially for very small geographies. So using this example I showed earlier, let's say there's a large retirement community where the blue star is here in area 2. So GeoCore is going to end up under allocating the over 65 population. So we looked at the allocation factor we came up with earlier on this was 39% of Cameron is in DeKalb County. So area 1, 39% of the whole of Cameron is in DeKalb County, and 61 is in Clinton. Well, you can't, all you can say is that over 65 is going to be the same. But we know, we just know from ground truthing that that's not true. So, it's going to underrepresent subpopulations that have an unequal distribution. Again, this tends to be more of an issue with smaller areas. With the larger areas, the spatial distributions, that kind of stuff tends to even out. But, there's no way of knowing really, other than like maybe looking at a map or if you know the area. Or whatever. So that's a limitation that I needed to point out to you. Very briefly, I'm not even going to really read this slide to you. It's interesting, though, that GeoCore has been around for ages. Originally written in Perl, it now runs in SAS. Hasn't changed much. The 1990 version looks almost exactly the same as the 2022 version, believe it or not, and it works pretty much the same. We've added many more geographies other than that, and we've changed it to running on SAS. A little bit of credit here, very briefly. All the original code written by John Blodgett, a giant in the census data world. Some of you probably may remember him. He retired some years ago. Yeah, just an incredible effort and a genius in census data. Personally, I've written many improvements and bug fixes. I created the 2014, 18, and 2022 versions. And finally, thanks to all of the GeoCore users over the years, because your questions and your input has been, invaluable to developing this application and keeping it going. That's it for me. I'm happy to field any questions, and I guess over to the mods.
Yeah, I appreciate it. Wow, that's a lot of great information. It's a really great source. We use it all the time. Census is just a really easy way to compare different geographies. It's a really remarkable tool, so thank you for sharing with that. The one question we did have was about how AFAC is calculated, but I think you went over how that was. I don't know if you want to elaborate very briefly while we're closing up.
Yeah, well, it's really it's a count. It's a count of population. So actually, I'm just going to go back to my slides and go back to the one that talks about it. Allocation factor. So yeah, how it's calculated is simply it's a fraction. It is a fraction of the intersection size divided by the total size of the source. Okay, so if you take Cameron, Missouri, again looking at this example, if you take any geography and there's two intersections with these two counties, you divide that out by whatever the sum of the blocks within that intersection, as opposed to the sum of the blocks for all of the city or whatever it is. And we just do that, I mean, all of that stuff happens on the fly in GeoCore every time it runs. We don't have like a list of allocation factors already pre-calculated somewhere. It's all done on the fly by adding up blocks. So the work that gets done ahead of time, the part of adding a geography to GeoCore that gets done ahead of time, is basically going to the block database and adding a column for that geography and just putting the ID for whatever geography that block belongs to in that column. So it can look, so basically, if I'm looking at ZICTAs, all I need to do is look in the block table for every ZICTA in the state of whatever, or every block in the state of whatever I'm doing that has a ZICTA, that and adding up the totals for each ZICTA. So that's where the numbers come from. We don't predefine them. There are a number of pre-made correlation lists out there, including many of the ones that that Jonathan's shop produces. GeoCore doesn't work like that. We produce our allocation factors on the fly from just adding up blocks. It's just basically massive amounts of addition with a single division at the end. Does that make sense?
It makes sense to me, absolutely. And just one clarification for when you were calculating getting data for within a distance of an XY, that's a Euclidean distance, correct? Not like a driving or practical distance.
Yes, correct. It's simply geometric distance using, Haber signs or whatever the spherical,
Sure.
formula. There's a formula in there that we use. But yeah, it's essentially Euclidean. Yeah, not driving distance. We couldn't possibly, I mean, yeah, we can't do that.
Well, yeah, once again, thank you so much for joining us and sharing that with us. And with that, um, thanks again, Glenn, and all of our other presenters for sharing with us throughout this whole two-day inaugural GeoForum. Here are some sites for further information about Census geospatial data, Census Academy, which will have this webinar on, as well as many others. A lot of great information they do over there. And if you have any questions, comments, or feedback about how this conference was run, not only for the presenters or for us at Census, but what you might want to see in the future, what either presentations or webinars you might be interested in us sharing. Thanks again so much for joining us. It's really been a thrill to see all of the interest in all of our data. Thank you.